So let's say I have a point. Let's say I have a plane pi and a point on the plane A. Then I've defined n to be orthogonal to this plane pi, and I want to point out that n is a position vector. N is not a free vector. Yeah, so if I then put another point that's on the plane, then the bound vector AB, whatever free vector this represents, let's say K, will be orthogonal to n. Yeah, so if I write that down, so if n I'm going to use freehand. If n is orthogonal to the plane pi, then if I choose 2 points on the plane pi, let's say A, B, then AB will be orthogonal to n as well, since they're on the plane. Since n is orthogonal to this plane, anything on the plane, n will also be orthogonal to that, any vector on the plane. AB is a vector on the plane, by the way. So we need to find an equivalent position vector to AB, as we can't do anything with AB and n at the moment. So since n is a position vector, we need to find an equivalent position vector to state what we just said before. So if I draw the plane again, put in my n. Even though I'm not drawing n as a position vector, like drawing the O and the n, I still want you to know that n is a position vector. I think it's really important to just keep stating that. So if I now draw P, draw my reference point, so P is now a position. This is my reference point O, and I drew a point P on the plane such that this vector here is the position vector of P. Then I draw R. This vector is now the position vector of R. So this vector here, which is on the plane, will be orthogonal to n. This is the same AB vector that we were looking at before. Now, what is the equation of, what is this vector in terms of R and P? Well, let's say I started off here, then I'd go minus P and I'd add R. So we can say it's R minus P, going in that direction. We could have said it was P minus R, but it'll just be going in the opposite direction. So it'll be starting there, minus R plus P. So now we know that R minus P is orthogonal to n. And from the scalar product, that means that we can write it now as R minus P yeah. Now, I'm not sure I went over distributivity. If I didn't, I'll just make another video going over distributivity. But what we can now do is we can distribute this n amongst the r's, the r and the p. So r dot n minus p dot n is equal to 0. I'm going to add p dot n to both sides, so I have r p. Yeah. This is now the vector equation of a plane. And if I just go over what our variables are again, so we have r, which is the position vector of the point r, where the point r is on the plane. N is the normal vector to the plane, the vector that's orthogonal to the plane. P is another point on the plane. Sorry, P is another point on the plane. So this vector here is the position vector of P, and N, we've just explained what N is. Now this equation only holds when P and R are both on the plane. Yeah. So if I go to the clear all pages, so we have r dot n is equal to p dot n. Now remember, these are position vectors. If n was a free vector, then we won't be able to do what we're about to do. So since these are position vectors, remember position vectors can be written in this new notation, so A, B, C, which is just a compact form of writing AI plus BJ plus CK. But it's just, if you have no idea what I'm talking about here, then you have to go to a previous video. So we'll say that n is equal to ABC. I'm not going to write n1, n2, n3. I could, but you'll see later on that this is more neater. It's more neater to write like this. Now we'll say that R is equal to X, Y, Z. P is equal to, yeah, we'll use P1, P2, P3. My handwriting's so messy. P is equal to P1, P2, P3. So now, if we do the dot product, we now have X, Y, Z dot with ABC, which equals P, which is P1, P2, P3, dotted with the N, which is ABC. Now again, this equation only holds if R and P are both on the plane. So now, if you remember from the dot product, when we do the dot product of something, we get a number back. So what I'm going to do is, I'm going to say that this is equal to D, where D is a number. So we're going to get a number back from this. So again, X, Y, Z, this is just to make it more compact. A, B, C is equal to D. So this is only true if X, Y, Z is on the plane. Hopefully that makes more sense. We figured out P1, P2, P3. We've done the dot product. We know that P is on the plane. Now we want to see if R is on the plane, some point R. So we do the dot. If R is on the plane, then X, Y, Z dot ABC will equal D. So hopefully that made a bit of sense, or hopefully you understand. If you don't, then just drop a comment and I'll just answer. I'm thinking of possible questions you could ask me. Okay, so one question you could ask me is, why did we do the dot product here? If you remember, the plane pi is defined by a point and the normal vector n. So if we have a plane, that means we have a point p1, p2, p3, and we have the normal vector abc, yeah? So then if I do the dot product of those, I get some number d. That's what I'm telling you. Now I'm telling you that if you want to find out if another point is on the plane, you do the dot product between that point and the normal vector. So if I just put these together, this is ax plus by plus cz, which is equal to d. Yeah? If you don't know what I did here, then again, you're just going to have to go check out a previous video that I did on this. But so this is equal to this. What this now says is that if x, y, z, the point x, y, z is on the plane, then when I do this equation, it will equal to d. So let's do some examples. So ax plus by plus cz is equal to d. Now ABC is the coordinates for the normal vector. So let's say we have our normal vector as 4, 5, 6, and d is equal to actually, let's change our normal vector to something easier. If we have our normal vector as 1, 2, 3, and d is 10, then let's just write that in. We have x plus 2y plus 3z is equal to 10. Is the point 1, 0, 0 on the plane pi? If I put 1 in, then I have 1 plus 2 times 0, 0, 3 times 0, 0, and that equals 1, which does not equal to 10. So this point is not on the line. Now, let's see. Is the point 0, 2, 2 on the plane? Okay, so x is 0, so 0 plus 2 times 2 plus 3 times 2. 2 times 2 is 4, 3 times 2 is 6, and that equals 10. So this point is on this plane. Do you see how we can use this equation now? If I now do 5x plus 6y plus... Okay. What's n? Remember, n is the coefficients of this equation here, so n is 5, 6, 7. Yeah? Now, I'm going to define two planes, and they're both going to be... I'm going to define two planes, and they're going to be the same planes. They're going to be parallel, and they're going to be the same plane. So x plus 2y plus 3z is equal to 1. 2x plus 4y plus 6z is equal to 2. Okay, so the normal vector for this is 1, 2, 3. The normal vector for this is 2, 4, 6. So the two normal vectors are parallel, and if you remember from the misconception video, this means that one vector might look like this, and the other vector, one vector might be there, but the other vector for P will be there. So since these two vectors are parallel, the two planes must also be parallel. And that means that they're either stacked on top of each other. I really can't draw planes, but if you imagine one plane being stacked on top of the other, or it means that they're exactly the same plane. It's pen. Now, how do we figure out if they're stacked on top of each other or if they're exactly the same plane? Well, if they're exactly the same plane, that means that whatever I multiplied by to get this plane, D must also be multiplied. Does that make sense? So let me show you. So we know that this normal vector is multiplied by 2 of that normal vector. So 2 times this is equal to that. But is it 2 times D as well? So we have 2x plus 4y. I'm multiplying the first one by 2 plus 6d. If I multiply d by 2, I get the second equation, which means that this is exactly the same plane. All the points on this plane also lie on this plane. Yeah? If you want to see a better way, if you want a better way of seeing why this is true, if you remember our equation ax plus by plus cz is equal to d, if I multiply everything by 2, I have 2 times ax plus by plus cz is equal to 2d. Yeah? I have exactly the same plane, I've just multiplied all the points by 2. So, I don't know if you have any questions on this, then just tell me. But I think this video is getting a bit too long.